Different teams have different infrastructure needs. Your analytics team might prefer AWS, while AI/ML workloads may thrive on Azure for their native integrations. Low latency applications, they often demand on-prem infrastructure. Now, however, each environment has its own tools, APIs, and operation practices, which makes it really difficult for platform teams to maintain consistency. Now, what if you could define and manage clusters across all these environments using a single, consistent, declarative API? In this demo, we will see how Nutanix Kubernetes Platform uses Upstream Cluster API to deliver exactly that, a CNCF-aligned, future-proof approach to multi-cluster management, whether it's on Nutanix, VMware, or the public cloud, all through the same set of declarative manifests. Hi, I'm Nimal with Nutanix Technical Marketing Engineering, and let's dive right in. Cluster API or CAPI is a Kubernetes subproject that allows you to declaratively manage the full lifecycle of clusters using Kubernetes-style APIs. Here, you can see that CAPI is already installed in the NKP management cluster, and platform teams can interact with it in multiple ways, through the NKP console, the CLI, or standard kubectl commands. CAPI enables NKP to provision and manage Kubernetes clusters running anywhere, on Nutanix, VMware, bare metal, or across public clouds like AWS and Azure. And it doesn't just stop at creating clusters. It automates the full lifecycle, including the configuration, scaling, and upgrades, all through consistent declarative infrastructure as code. Now let's take a deeper look at CAPI architecture. So you have the controllers that we saw earlier at the top level here. The CAPI core controller coordinates the overall cluster and machine lifecycle. Then you have the providers, which are modular components that plug into the CAPI framework to support tasks in the cluster lifecycle. So these controllers create custom resources to perform these tasks, and here are some examples. The cluster resource is the top level resource, representing the desired state of the Kubernetes cluster. It acts as the anchor for all other resources related to the cluster. A provider-specific resource such as AWS cluster or Nutanix cluster is created that describes the infrastructure-specific configuration for the cluster. Now, to define the configuration for the control plane nodes and to provide the bootstrap configuration for both control plane and worker machines, kubeadm is commonly used, now, although there are other providers available too. Now, resources such as machine deployment manage sets of worker nodes, providing rolling updates and scaling, while provider-specific machine templates like Nutanix machine template define how each of those nodes should be provisioned, such as the VM hardware and the image configuration. Now, this can start to look complicated if you have to manage these manifests for multiple clusters and do it at scale, right? Now, the good news is that if you're running on Nutanix, NKP uses a powerful feature in CAPI called cluster class. As a platform engineer, cluster class lets you define infrastructure templates which has the structure and topology of a cluster. So all the complexity like VM sizing, networking, storage, the control plane design, CNI, the CSI configuration, all of this is encapsulated in reusable templates. Then individual dev teams can create clusters with just a single cluster manifest, tweaking only the parameters that they want to change.
So now let's get to the fun part, the actual cluster provisioning. I'm logged into my Ubuntu jump box, and the first thing I want to do is list all the Kubernetes clusters I'm managing. This command here lets me view all clusters across all namespaces, just like how I would list pods or services. What's nice is that it also shows me important metadata, like the Kubernetes version each cluster is running on. Now let's take a closer look at the spec for one of these clusters. As you can see, it is a standard Kubernetes style manifest where the kind is set to cluster. Under metadata, we have defined the cluster name and namespace where it will be created. The spec section is where the real power lies. This is where we define the cluster parameters, everything from networking to infrastructure to how the nodes are configured. For example, we specify the pod and service subnets, the API server endpoint, and the infrastructure provider, which is Nutanix in this case. We can also choose the CNI plugin like Cilium and configure the CSI driver. The CSI settings let us define whether we want block storage or file storage, enable auto expansion of volumes, and more. Now going further, we can set granular details for the control plane and worker nodes separately. Things like CPU, memory, disk size, and even the OS image. Here I'm using Rocky Linux, but Ubuntu or Rail can also be used, depending on your workload needs. So what's the key takeaway here? The entire Kubernetes cluster configuration, networking, storage, infrastructure, the node specs is defined declaratively in a single file. It is portable, it is repeatable, and fully automatable. Now let's look at a couple more cluster specs. This one here is very similar to the previous example, but notice that the infrastructure type here is vSphere instead of Nutanix. And here's another one. Again, a very similar structure, but this time the cluster is on AWS. So the value that you get here is that all the three clusters, Nutanix, vSphere, and AWS, are defined using the same cluster API schema and managed by the same NKP management cluster. This means that your platform team does not need to learn a different tool or workflow for each environment. Whether you're deploying to private infrastructure or public cloud, you're using the same declarative model, the same CLI, and the same lifecycle controller. So how do we actually create a cluster? Just like any other Kubernetes resource, with a simple kubectl create command. In this case, I'm creating a cluster called AHV demo. Now let's jump into the NKP console and take a look. Under the clusters tab, we can see that the AHV demo cluster is already being provisioned. Now what is really valuable here is that we also get visibility into the platform services that are being deployed automatically, like monitoring and logging, all out of the box. Now this saves a ton of time and effort, and it means that every cluster we create is ready for production from day one.
So to recap, we used NKP and Cluster API to provision Kubernetes clusters across different infrastructures using a consistent declarative workflow. It's not only through the CLI, but you can perform these operations from the UI as well. Now this level of consistency is incredibly powerful. It reduces operation overhead, minimizes risk, and it makes it easier to apply things like GitOps, policy enforcement, and automation across the entire fleet of clusters. Thank you for watching and stay tuned for more.